Welcome to section 3.2. So we continue our discussion about derivative. We will see more properties of the derivative. Learning objectives are the following. So again, we'll discuss a few more examples of calculating derivative. And then we consider when does a function not have a derivative, right? What does it mean to not to have a derivative? And then we compare differentiation, so differential functions, and the continuous functions. Continuous functions we saw in the previous chapter. Right. So here's the definition of the derivative one more time. So to find the derivative, so this is the f prime, right? You can read it as f prime of x, or you can read it as derivative of f of x, etc. It's nothing but the limit at h goes to 0, f of x plus h minus f of x divided by h, provided that this limit exists, right? When the limit exists, we call the function is differentiable, right? So this f prime exists, we say that it is differentiable at point x. We also say if the f prime exists at every point in its domain, then we simply call f differentiable without mentioning where it's differentiable. If we don't mention where it's differentiable, it simply means it is differentiable in its domain. Okay, as mentioned before, so alternative formula for the derivative is f prime of x, limit as z goes to x, f of z minus f of x divided by z minus x. Now, there are several different notations to indicate a derivative. So one of the common one is f prime, and another common one is y prime, or and another common one is dy dx. So very nice representation, especially when we start discussing integrals. This dy dx idea becomes very important, and there are, you can see, other ways of representing the derivative. Okay, let's do an example. So we would like to differentiate f of x equal to x over x minus 1. It doesn't say at which point, so we just differentiate at every point. So our x0 is x, right? So what is f prime of x? Well, this is nothing but limit h goes to 0. Here, f of x plus h minus f of x divided by h. Right? What do we have? What is my f? It is x divided by x minus 1. So I substitute x plus h. I get x plus h. Here I get x plus h minus 1 minus, in place of f of x, I simply write x minus 1. Now we need to bring to common denominator, right? So this is equal to limit h goes to 0. Okay, so at the top, what is the common denominator? Well, common denominator is x plus h minus 1 multiplied by x minus 5, right? And then at the top, x plus h multiplied by x minus, so x plus h. So I'm kind of doing carefully so that you can see all the details. Minus x, so you multiply x by x plus h minus 1. So that's simply the top, the numerator. Now denominator is simply h, right? Okay, so let's see what we get. So here this is like h over 1, so you flip it, multiply by the top, you get at the very bottom we get h, x plus h minus 1, x minus 1, right? Now what do we get at the top? So you expand the parentheses, so you get x squared minus x plus hx minus h, and multiplying out the second one, we get minus x squared minus xh plus x, Right, hopefully there are some cancellations. So x squares cancel, plus xh minus xh cancel, plus x minus x cancel. So I left with a single minus h. Well, then this minus h will, okay, let me not cancel there. Let's not cause confusion. So what we get is at the top I left with minus h. At the bottom I have h, x plus h minus 1, x minus 1. So h is cancelled. What we left is, here it's 1, or minus 1. Here I get x plus h minus 1, x minus 1. So letting h go to 0, x plus h minus 1 goes to x plus minus 1. So the bottom becomes x minus 1 squared, right? So I get minus 1 over x minus 1 squared. So that's the derivative of x over x minus 1, as far as x not equal to 1, right? Because at x equal to 1 it's not defined. More examples. Let's find the derivative of square root of x when x is positive, because when x is negative we cannot do it, right? It's not defined. It's not even defined, right? So f prime of x, or if you like, square root of x prime, what is it? Limit x goes, sorry, h goes to 0. I could also use the other definition though. But anyway, h goes to 0. Here square root of x plus h minus square root of x divided by h, right? Okay, so how do we handle the square roots? Well, one option would be, let's sort of rationalize the numerator. So let's multiply by its so-called conjugate, by plus of it, and see whether that helps. So we don't know if it helps, right? So what do we see at the top? So it resembles the following formula, right? So a minus b, a plus b, right? So where a is like a square root of x plus h, and b is square root of x. We know that this formula is a squared minus b squared, right? So h goes to 0. Here at the top, I'm left. So you square, so it becomes like x square root of x plus h squared. So square and the square root, they cancel. So you're left with x plus h. And the square root of x, so it becomes square of the square root of x. So again, it's square root of x squared, which is x. And at the bottom, I am left with h and this term. Okay, so x is cancelled. I left with h at the top. Here I also have h. Luckily, they cancel out. And I will get something nicer, right? So I get 1 over x plus h in square root plus square root of x. Now if you let h go to 0, this x plus h goes to x. So this goes to 1 over x square root of x plus square root of x, so this is 2 square root of x. So that's the derivative. Right, now this was for part A. Now let's do part B. Let's see if the space permits. So I want to find the tangent line at x equal to 4. So which means first I need to find the slope, right? Slope. So slope is f prime of Okay, so to calculate the slope, it's f prime of 4, right? Because we are looking for the tangent line x equal to 4. So we already have the f prime derivative. It's 1 over 2 square root of x. So this is nothing but 1 over 2 square root of 4, which is 1 over 4. So we found the slope. Now, what was the tangent line formula? As you remember, this is y is equal to the slope, which is 1 over 4, x times b, right? Now, how do we find the b? Well, what happens as x equal to 4? If x equal to 4, what is y? Y is square root of 4. This is 2, right? So this x equal to 4, y equal to 2 needs to satisfy this equation. So you let y equal to 2 1 over 4 x equal to 4 plus b, so we see that b is equal to 2. Hence, the tangent line is 1 over 4x plus 2, right, at the point x equal to 4. Let's consider one more example. Y is equal to absolute value of x, modulus x. This is a somewhat special kind of function because it gives us some interesting fact about when we fail to have a derivative. Okay, so let's go ahead. So it said investigate derivative, so it means I need to again take x to be sort of arbitrary. So let's first start it. So I can say f prime of x, limit as h goes to 0. Here I get x plus h minus absolute value of x divided by h. Now, how do I handle x plus h absolute value minus absolute value of x? Do they cancel out, etc., right? So it really depends. So if x is positive, right? If x is positive, then for h sufficiently small, it goes to 0. X plus h is also right. Then x plus h also becomes positive for h small. So this means, what do I get for this? This means this limit becomes nothing but x plus h minus x divided by h. So x cancel. This is limit h over h. They cancel, right? So this is simply 1, right? So 1. Well, if x is negative, then again, if you pick h is sufficiently small, then x plus h still becomes negative, right, for h small. So in this occasion, both of them are negative terms, so I need to multiply by minus to make the absolute value positive, right? So in this occasion, what I get is limit as h goes to 0, I get minus x plus h, I get minus, and I have another minus, right? I'm trying to make all these things positive, right? So what happens is, okay, let's write it. So here I get minus x minus h. Here I get plus x over h. Again, x is cancelled, but in this case, you see that I'm getting minus 1, right? So in conclusion, what I can say that f prime is 1 or minus 1. It's 1 if x is positive. It's 0 if it's negative. So the question remains, what is the question? What happens at x equal to 0? So let me clear. So at x equal to 0, right? Well, what is the derivative, right? Let's see. Limit h goes to 0. I write the same thing. So I had x plus h. Now I have 0 plus h. So it's like h minus 0 divided by h. So this is nothing but limit h goes to 0, absolute value of h over h. All right, what happens? If h goes to 0 from left, so let's calculate two-sided limits, right? If I'm approaching from left, then my h is negative. So which means I need to multiply to make it positive, right? So this becomes minus h over h. H goes to 0 from left, so this becomes minus 1. Now let's approach from right. If I approach from right, then h is positive, so this absolute value of h is simply h. This is h over h. So this is simply 1. So left hand limit and right, so this is my left hand limit, right? Left hand limit. This is my right hand limit, and they are not equal, which means the limit doesn't exist, right? So at x equal to 0, limit does not exist. So derivative doesn't exist, right? So no derivative. So in other words, at x equal to 0, no derivative, no derivative. Let's sketch the graph. Let's sketch the graph. So the graph looks something like this, right? We already know what it is. It's like x. If x is positive, it's 0. If x is 0, it's minus x. If x is negative, so that's the graph. And as you can see, this is a 45 degree because we found the slope to be 1. Here it's again 45 degree because we found the slope is minus 1. And why 45? Because tangent to 45 is 1. Here it's, sorry, then this would be, you need to look at this angle. Anyway, so we found that at these points the slope is 1, and at these points the slope is minus 1. However, at 0 origin it doesn't exist, right? Think like this. Can you sketch a tangent line to the graph at the origin here? Can you find a tangent line? Well, you see there are lots of options, right? This can be a tangent line, this can be a tangent line, that can be a tangent line. There are lots of tangent line, right? The infinite limit tangent line. It means the slope is not well defined. It's not defined at all, right? So slope doesn't exist. So this is a corner, right? Here the function is very nice. Here it's very nice, but here we have a corner, right? Like this corner. So whenever you graph the function has a corner, it kind of suggests that there may not be a derivative there. Okay, so existence of derivative means your function at that point is smooth, right? That is nice. The graph looks nice when there is a derivative at that point. So in the last example, we saw the case when derivative fails to exist at one point, right? At 0, because it has a corner, right? So this is the first instance. So your function is represented in blue, and we see that there is a corner, and at this corner we have lots of options for the tangent line, etc. So it fails to have a derivative, right? So this is about not having derivative. And another option could be like if you have a cusp. So your slopes might be sort of blowing up, right? If the slope blows up at that point, in other words, if the limit becomes plus or minus infinite, the limit in the definition of derivative, then again we fail to have derivative. Or in the third case, it's also like having a slope. So again, the slope at certain point may become infinite. So again, it fails to have. Another way is instance is discontinuity. If the function is discontinuous like this, right, John, then how do you sketch a slope, right? I mean, again, it's not well defined. Or again, it might even have a very simple, like removal discontinuity. Again, it's not clear how you sketch the tangent line at that point because the point is not there, right? Its point is somewhere above or etc. Or it might be oscillating again. So all these behaviors fails the derivative. So for such instances, the derivative doesn't exist. So finally, we discuss the relation between differentiability and the continuity. So differentiability is much stronger condition than continuity. So in particular, it means if the function is differentiable at a certain point, then it is automatically continuous. Okay, but not vice versa. So here's the theorem. So let's first prove this theorem. So differentiability implies, so if f has a derivative at certain point, then f is continuous at this point. How do we check the continuity? Okay, so let's prove it. Well, I need to show, I need to show that f of c is equal to limit as x goes to c of f of x, right? So let's investigate this right hand side. So let's start with limit as x goes to c of f of x. Well, let's make it look like a derivative. Oh, sorry, this goes to c. I could write like f of x minus f of c plus f of c, so nothing changes. And then I can, sorry, I need to write this a little further. So plus f of c, you will see why. Now let's divide this term by x minus c times x minus c, right? You multiply and divide, nothing changes. Now look at what happens to this term. What is this term? This is another definition of the derivative, right? So, and we already know that derivative exists. So if you let x go to c, this particular part goes to f prime of c, and we know it exists, right? We know it exists. So then we can write it as limit x goes to c, f of x. Because this limit exists, we can split the limits. We can write x minus, we can write like limit of this times the limit of the second expression, x goes to c, x minus c, and we also have the limit of f of c, but that's not very, it's just a constant, right, f of c. Now the first one goes to, as we said, f prime of c. The second one, x goes to c, means x minus c goes to 0, plus this is f of c is just a constant, so this is simply f of c, right? Hence this is f of c. This is what we wanted, right? We want this identity. And indeed, we started from right hand side, we arrived at the left hand side. So we conclude, so f is continuous at x equal to c. If this derivative exists, right? If the derivative exists, we assume the derivative exists and continuity. One last thing is why the converse is not true. Can we say that continuity implies the existence of derivative? No, no. Let me spare this space to explain why. In fact, we already saw the example. We saw this example, right? This is an absolute value function. We know that absolute value function is continuous. You can also see it from graph, right? No interrupts, so no interruptions. So this is a very nice graph. I mean, it's a continuous graph. So this is a continuous function. However, we saw that at x equal to 0 at this point, while it is continuous, it's not differentiable. Okay. So long story short, the continuity does not necessarily imply differentiability. However, differentiability always implies continuity.